happy to have all of you guys back here to start a new semester. And our first speaker here is Yin Lee from Columbia University. He's going to tell us about the Hypertoric, convolution algebra, and
thank you for the introduction. So I'm going to talk about some results on the symplectic geometry of hypertoric varieties. So first recall that a d-dimensional hypertoric variety is defined as the hypercalar quotient. So you take the vector space Cn and you take its cotangent bundle and you quotient by a torus of, sorry, there should be 4 slashes of dimension n minus d. So I choose this dimension n minus d because I want my hypercalar variety to be d-dimensional. So this is the same as the algebraic symplectic quotient. So I'll explain notations later. So this mu c is a complex moment map on the cotangent bundle of Cn. So in particular, this lambda c belongs to the vector space, complex vector space of dimension n minus d. So this T is the Lie algebra of this torus. And there is also additional parameter lambda r, which belongs to the real Lie algebra of the same dimension. So in particular, this lambda c is a vector in Cn minus d, and lambda r is a vector in In minus d. The geometry of this hypertoric variety, so let me denote this thing by M, actually depends on 2 parameters, lambda r and lambda c. Because I'm studying the symplectic geometry of this hypertoric variety, so in this talk, I'll mainly use lambda r equals 0, and lambda c can be generic. So this will equip this hypertoric variety, lambda r, lambda c, with the structure of an R-phi variety. So in particular, it cannot contain any like complex submanifold. So for example, we have cotangent bundle of Cpn, cotangent bundle of n copy of P1, and the Mionov fiber associated to an AM singularity, which is maybe many of you are familiar, but I just want to write down the definition: x squared plus y squared equals c minus 1 to the power of m inside C3. So you can see this is a affine hypersurface inside C3 because of the algebraic structure we have just equipped this thing with.
So, sorry, you specialize lambda r to 0 already?
Yes, lambda r is 0.
Lambda r to 0.
Yes.
And when you write P star Pn, you mean the smooth manifold with the
right. Right, that's true. Yeah. So for example, T star P1 should be understood as T star S2. So as we know that there is somehow a combinatorial data which can be used to describe the geometry of hypertoric varieties, and such a combinatorial data is called hyperplane arrangement. So hyperplane arrangement means a collection of real hyperplanes inside this vector space, because our hypertoric variety is d-dimensional, so it's inside Rd. So, for example, if we take cotangent bundle of Cp2, then the corresponding hyperplane arrangement is this one. So you can see the P2 from this picture, which is just this triangle, which is a moment polytope of P2. For the study of symplectic geometry, I'll need an additional piece of data, which is a polarization. So polarization of a hyperplane arrangement is, roughly speaking, so I'm not going to write down the formal definition, a choice of an additional hyperplane inside this picture, which is in some sense have different slopes with all the other hyperplanes. So I'll denote this additional hyperplane by Koszul. And this choice will give you an additional information, which is the notion of bounded chambers. Of this hyperplane arrangement. So I'll call this hyperplane arrangement V. So the definition of bounded chambers means that if you move this additional hyperplane, you will see that if you move this hyperplane to a certain position, then it will be disjoined from certain chambers inside this hyperplane. For example, in this picture, if I move this hyperplane to this direction and I move it to infinity, it's going to be disjoined from this chamber, and this chamber. So these three chambers are bounded chambers inside this picture. You can choose like different polarization, and it will give you different bounded chambers. So from this data, you can define, from this combinatorial data, you can introduce some kind of invariants in algebra, which are the convolution algebras in this title. So this is called Hypertoric convolution algebra because they're associated with hyperplane arrangement.
Just to be precise, doing centralization, you mean hyperplane together with a half space, the choice of half space.
Right. So the convolution algebras, there are two convolution algebras called AV and BV. So these convolution algebras are introduced years ago by Braden-Licata-Proudfoot-Webster. So let me recall the definition of A. So AV is the quotient of a path algebra of a certain quiver QV, which I will specify later, tensor with this symmetric algebra over a certain vector space VK star. So let me tell you what is VK. So VK is just a subspace of Kn, with K being a field. I think in this talk I will specify this K to be a field of characteristic 0. For example, the most natural choice is K to be the real numbers. So this QV, this quiver has vertex set, the set of non-empty chambers So these non-empty chambers are called feasible chambers. The reason that we need an additional notion called feasible chambers is that in general, these chambers are like labeled by, I should say labeled by sign sequences. So if you have a psi for each hyperplane, and every psi sequence of this form, which means you have a real number for every hyperplane. Sorry, not a real number, but a plus or minus. So every alpha I is equal to plus or minus. So you have this thing, and this thing is equivalent to specifying a chamber. But sometimes when you specify a psi sequence, it could correspond to an empty chamber. That's why we have the notion of feasible size sequences. So for this talk, you just remember that it contains like all the chambers in this picture. You have these 3 bounded chambers, but there are 4 unbounded chambers. So altogether, you have 7 feasible chambers. And arrows, so this is a vertex set, and the set of arrows P alpha beta for any chambers alpha and beta, which let's just say share a common face. For example, if you have these 2 chambers, there is this common light segment here, and for these 2 chambers, they're nearby chambers. But for these 2 chambers, they are not, because their intersection is kind of codimension 2. So you have this quiver, you can define its path algebra, and you need to quotient by the relations mod out by the relations.
So when you say face, you mean real codimension 1?
Right, real codimension 1. Or you can like more rigorously, you can use this size sequence interpretation. There is exactly 1 different size.
I see. Okay.
Yeah. So first you have this E alpha, which is an idempotent. You need to model this idempotent for every chamber which is non-empty but not bounded. So this F means feasible. And this curly B means bounded. So for our definition of this algebra A, you only take into account of the information of bounded chambers. That's why you model out all the idempotents for the unbounded chambers. And you have this relation P alpha beta minus P alpha delta P delta gamma for the following 4 chambers. So this is alpha beta delta gamma. So as long as you see these 4 chambers which are somehow form this structure, alpha is near to beta, beta is like nearby of delta, delta is nearby of gamma, and gamma is nearby of alpha, you quotient out by, sorry, I should say P alpha beta, P beta gamma. So you quotient out by this quadratic relation. And because you quotient out by this quadratic relation, you get to the conclusion that this is a quadratic algebra. And the third relation is that you need to quotient out by P alpha beta, P beta alpha minus Ti E alpha, where Ti is a variable here in the symmetric algebra. So alpha beta are any 2 feasible chambers such that alpha and beta are nearby. So I will use this notation alpha 2-headed arrow beta to denote the fact that these 2 chambers are nearby to each other. Means they share kind of codimension 1 face. Okay. So this is the definition of the convolution algebra A. There is also a convolution algebra B.
And you use Ti as a parameter.
Ti is a variable inside this symmetric algebra. It's a polynomial, 1 variable inside this polynomial algebra.
What is the VK?
VK is a d-dimensional vector space inside this n-dimensional vector space K. So basically what VK tells you is that all the kind of linear coefficients of your hyperplanes inside the arrangement, you have the slopes of different hyperplanes, and this VK, you can regard it as a matrix D times N matrix, which tell you like all the kind of the coefficients before the like linear variables, and we record it inside this vector space V.
More explicit about how you construct VK, or what's the definition?
So the data of
Did you get a copy of our algebra for non-commutative variables? Is that what it's in?
So this V you get a, so this VK is a like quotient of the like polynomial algebra in n variables, right? This Ti is like 1 variable inside this Kn.
By what?
It's
You symmetrize with respect to what?
It's a symmetric algebra over this Vk, right? You quotient by like all the linear forms which annihilates Vk. So Vk is a so you know that the data of a hyperplane arrangement.
Would you do an example? Just something for example. A good example is.
For example, this V.
AM surface maybe.
For example, this Vk is like in this CP2 case, this Vk is R2 inside R3, right? And you need to record the coefficients of the hyperplanes. So one hyperplane is like 1 0 0 0. Sorry, it's right.
What's the definition of VK?
VK is just I mean, you know, the data of a hyperplane arrangement, a polarized hyperplane arrangement is equivalent to the data of specifying a vector space, d-dimensional vector space inside Rn, and eta is a vector inside Rn quotient by phi. You know, basically this VK tells you like what the coefficients between, because in this case you have like ax plus by equals some constant, right? This Vk tells you this a and b coefficients, and this c is recorded in this vector eta. So there is a grading on this algebra AV by setting the arrow P alpha beta to have grading 1 and the formal variables Ti to have grading 2. So I think there is also a geometric interpretation of this algebra by passing to the Koszul dual side. So it is known that it's a theorem due to these people, Braden-Licata-Proudfoot-Webster, that this AV is Koszul dual to A associated to the so Gale dual hyperplane arrangement of V. Sorry, it's the Gale dual. So the most convenient definition of the Gale dual is that, so if you have this V specified by this data, a d-dimensional subspace V, a vector eta, and another vector Kc is a polarization. So this V check is going to be, you take the orthogonal complement of V minus Kc and minus eta. So to give you an example, you have this T star CP2 example, which is arrangements of 3 hyperplanes in R2, and its scale dual is going to be 3 points on the line. So it's a 1-dimensional hyperplane arrangement with 3 hyperplanes. And you have these bounded chambers in this picture. And here you have, so for example, we choose a polarization like that. And here we choose the polarization which is specified direction. So which is to specify this direction. Then the bounded chambers in this picture are these 3 chambers. So if you take this hyperplane arrangement and look at this, the associated convolution algebra A, it's going to be Koszul dual to the same convolution algebra but defined for the Gale dual hyperplane arrangement. So definition, so the second algebra, convolution algebra BV, is by definition just the algebra A associated to the Gale dual hyperplane arrangement. But there is a geometric interpretation of this convolution algebra BV, which is additively, this BV is just isomorphic to the direct sum over all the bounded chambers of this X alpha beta K with grading shifted by D alpha beta. So let me tell you which is X alpha beta. So as I have said, the hyperplane arrangement, you look at this hyperplane arrangement, you have bounded chambers, and every chamber will give you a toric variety, which I will denote by X alpha. Or in other words, you can view it as the core, you can view this alpha, X alpha, as cause of the partial resolution of singularities from this M. As I said, I use there lambda r equals 0, but here I need to use generic parameters lambda r and lambda c, or you can use lambda c to be 0, so that these cores are going to be complex subvarieties. So this is a resolution of singularity over M0, 0, where you specify all the parameters to be zeros, and you have a singular point. And this map is going to resolve this singular point, and when you resolve this singular point, you get these toric varieties. X alpha beta is defined to be X alpha intercept with X beta, and we allow X alpha and beta to be the same, and D alpha beta is the dimension of this X alpha beta. So this thing, this direct sum of cohomologies, can be equipped with the structure of a convolution product. Which is you take, for example, X alpha beta, and you do cup product. Cup product. And you do Poincare duality. And you do a push forward on homology associated to the inclusion X alpha beta to X alpha or X beta. You will get some class inside this X alpha or X beta. And you do Poincare duality again. So you will get a class inside the cohomology of X alpha or X beta. So this is a product on this algebra. There is a subtlety, which is a choice of orientations on this X alpha beta, but I'm not, for simplicity, I'm not going to talk about this subtlety. It basically affects the size of your product, so you need to choose the correct size, but the original size, original orientations of these intersections X alpha beta are not the correct size if you want to recover the convolution algebra BV, but you need to add a twist to the orientation so that all the sides match with the convolution algebra BV. So this is basically some preliminaries of the stuff that I'm going to talk about. So now let's right. Poincare duality and push forward of homology. Inclusion, there is this inclusion, and you use this inclusion to push forward.
What is the predicate now?
eta. So definition of eta is that it's a vector. You see, it's a vector Rn quotient by V. So what it means is that you for example, you have this R2, and you have this hyperplane, and here you have a additional vector, right? You have additional vector, and this eta records this additional vector here.
So it's like the Hyperplane, you start with Hyperplane, you have this coordinate Hyperplanes. Yeah. You projected the quotient by the vector subspace D, and then you have the image. So this interface page and which fiber
So your hyperplanes are like affine subspaces, right? So vector space V specifies the linear part, and this eta specifies the affine part.
Here for the alpha beta, like, what do you mean the alpha beta in BV?
So alpha beta in BV is that you have this choice of your polarization, right? When you specify this polarization, you have the bounded chambers. And these bounded chambers are, I label these bounded chambers by this alpha, beta, gamma.
Okay, they're done.
Yes.
Okay.
So let me just keep this as a like standing example, right? This is a hyperplane arrangement. C moving in this direction, and we have like different chambers, but different chambers correspond to different size sequences. So here is minus, plus, 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 minus, minus, plus, plus, minus, plus, plus, plus. So this size has something to do with the size of this. So this C can be realized as a kind of linear function on these chambers, and this size has to do with the size of this. And this boundedness corresponds to the fact that this linear function is bounded on this chamber. So this is T star P2. So let's get into the like main issue of this talk, which is the symplectic geometry of these hypertoric varieties. So as I have said, I have like specified the structure of this hypertoric variety, so that this is an R5 variety. So because we want to talk about symplectic geometry, so we assume that this is a smooth R5 variety. So this smoothness condition can be specified in terms of the hyperplane arrangement. You can impose certain conditions on the hyperplane arrangement so that this thing defines a smooth R5 variety. So in particular, this is a Weinstein manifold in the sense that you have a well-defined handle-ball decomposition. Each handle carries its symplectic structure, and you can use this symplectic handle decomposition to construct this thing. In particular, it means that like it's kind of its skeleton or its like topology is kind of subcritical. You cannot have like cohomology, which is larger than middle dimension of this variety. So this polarization C singles out a collection of real Lagrangian submanifolds, because I only care about real symplectic geometry. L alpha with alpha corresponding to bounded chambers inside this MV. Okay. This L alpha just like X alpha. X alpha comes from the resolution of singularities. But now because we do a hyperkähler twist by specifying lambda r to be 0. So what we get is that these complex subvarieties, toric subvarieties, become real Lagrangian submanifolds of this hypertoric variety. That's why we have a well-defined Lagrangian skeleton, which is given by the union of this L alpha. And we take the kind of, because it's a smooth R5 varieties, there is a like exhaustion function. So you can talk about what is the ideal boundary of this smooth R5 variety. So I'll denote this thing by partial infinity, which means the boundary at infinity. So this is ideal contact boundary. So this is in fact a contact hypersurface inside this smooth R5 variety, and you take the intersection and we will denote this thing by FB. So as we can see that only non-compare bounded chambers can contribute to this FV, because if it's compared, then it's not going to intersect with this ideal contact boundary. So what we get is the data. So starting from the data of a polarized hyperplane arrangement, what we get is a stopped Weinstein manifold in the sense of symplectic topology.
Can you maybe just give us a little more background?
Yes.
I'm also starting to lose track. So originally, this Webster and others, they did what kind of calculation to obtain these algebras? So at first, right, in particular, right, you actually just stated what A is. You didn't, as far as I got, you didn't actually explain how they got it. And secondly, you're telling us that okay, so given one of these hypertoric spaces, you told us how to write down A, right?
Yes.
And now you said if I have a pair of these hypertoric spaces like the Higgs branch and the Coulomb branch of a billion 3D gauge theory, that they, as Webster tell us that A and HX are dual.
Right.
You also tell us how to compute B from the original, say, Higgs branch.
Right.
But you didn't tell us how to compute A from the same branch. What was their thinking of?
So A is you can take the quadratic dual of B, right? Both A and B are quadratic. I said A is quadratic by definition, but B is also quadratic. And because B is just this.
So you say, so it's enough to give one geometric
right.
Which is what they did? Is that what they did?
You mean the original paper?
Well, yes. I mean, not
yeah, yes. You only need to compute one of them, right? The other one is by quadratic duality. Yeah. But geometrically, they correspond to different versions of Fukaya category, as we will see. So this is so from this data we get a stopped Weinstein manifold. So I'll tell you what is a stopped Weinstein manifold.
Definition of our second definition is in homology of X alpha beta. Is that shift degree up or down by d alpha beta?
It's shifted up by d alpha beta, right?
So X alpha beta has dimension 2, complex dimension 2. Is X alpha beta, when you say dimension, is that the real dimension or complex dimension?
They are the same. I mean, it's you for real dimension, you realize it as the intersection of the hyperplanes of the chambers. For complex dimensions, the intersection of toric varieties, the dimension.
Okay. So this is like in a positive dimension.
Right. So I should say this both alpha and beta are positively graded, non-negatively graded, I should say.
Whichever geometric definition is it somehow natural? I mean, these are not coherent sheaves. You said they're constructible sheaves. So if you give it to a person who does constructible sheaves like Pang will say,
it's constructible. You take constructible sheaves on this X alpha beta, and
so that is a bit of a strange operation, right? Because you say it's not a. But so this is the prescription that was given, and this is the prescription that existed before your work, and you're going to give us another way.
Yes. Yes. So all these things are basically due to the BL, like yeah, they define all these things, and they have this somehow the Koszul duality interpretation, and they prove that these are like standard Koszul algebras. Yeah, and they also have some like analogous comparisons with category O. They call this Hypertoric category O. So we have a stopped Weinstein manifold. So a stopped Weinstein manifold is a Weinstein manifold with Legendrian, additional Legendrian submanifold on the boundary. So originally you have a Weinstein manifold. You can take its ideal boundary.
Sorry, can I just ask just one more background question about actually that work? So presumably for with a T star P1, right? Then this is supposed to get related to representation theory of SL2.
Right.
Did they spell the story out for just one kind of representation, or one set of branes, one set of algebras in Cheuk, or there is, in principle, whichever prescription tells you how to calculate V from that space, would it know what to do if I chose a different class of object that would generate your category in retrospect?
So I think all the objects correspond to the choice of a polarization. You can choose different polarization, you get different set of objects, but otherwise I think that's not included in their paper.
Okay, so the only things they did were things that looked like this.
Right, right.
So they don't even, is there in principle a definition what I'm asking is that guy is natural? I mean, the definition is geometrically natural. If I picked a different set of generators, would there be an analogous definition, or?
There is, I think there is. It's natural, but I mean, all these papers are like more than 10 years ago, so you can't expect too much. So this is a contact manifold, and the stop. So M, let's say a stop. Let's say F. Stop F is an additional data, which is a Legendrian inside this contact manifold. So when you compute, for example, when you have like a two Lagrangians inside the cylinder, so this is, what I mean is that this is cylinder. This is not a Lagrangian we are looking. So for example, we have one Lagrangian and we have another Lagrangian, and you choose some Hamiltonian which wraps it. What you do is that you basically adding a stop is like to specify some, for example, a point on this contact boundary. In this case, it's S1. So then when you look at for example, if this green Lagrangian intersects with boundary at this point, so this is a stop, and this is your yellow Lagrangian. So suppose this is the direction of your reap flow. What this stop does is that when you wrap around this boundary of your cylinder, when you have a stop, you need to stop wrapping. So originally there is a kind of a reap chord from this Lagrangian to this one. But when you put a stop there, this is no longer a generator inside your wrapped Fukaya category. So what the stop does is that you have like fewer generators inside the Fukaya category, but somehow the stop also adds more generators to your Fukaya category because there are like linking disks associated with these stops. So this is a very brief recall of the notion of this stopped Weinstein manifold. So there are two versions of Fukaya categories, two very natural versions of Fukaya categories, which can be associated to this stopped Weinstein manifold. The first one is the infinitesimal Fukaya category. which we'll denote by f of this mv, fv. So infinitesimal means that you don't wrap at infinity. What you do is that you do a small perturbation. So basically, infinitesimal Fukaya category looks like this. This is your L1. And when you define this morphism between L1 and L2, right? Say L2 is like this. So at infinity, what we do is that we perturb this L2 a little bit so that it transfers to L1 at infinity, but you don't do wrapping. So this is the infinitesimally wrapped. But there is another version of the Fukaya category which is partially wrapped. So partially wrapped, as I said, just like on the cylinder, you can do fully wrapping, but as long as you meet a stop, you need to stop there. So somehow the partially wrapped Fukaya category is you allow all the wrapping except for those which intersect with the stop. Both of these are like A infinity categories and graded by integers. Okay. So I have introduced the corresponding notion. I mean, these notions you should think of them as corresponding to the notion of the two convolution algebras BV and AV. With the infinitesimal one correspond to BV and the partially wrapped one correspond to AV. Actually, this is, I say this is a conjecture due to. You mean this D alphabet? Yes, it should be the codimension, right? Right. Wrapping means you, for example, you have a Lagrangian and you use a quadratic Hamiltonian. So suppose you have a Lagrangian and somehow you want to, so you know that in the standard definition of Lagrangian flow cohomology, what you do is that you do a Hamiltonian perturbation, a completely supported Hamiltonian perturbation. So what you would see is that you would get something like this, right? But wrapping is that, I think what you would see is that, so you, for example, you perturb along this part, but because it's completely supported, it does not affect the part at infinity. So for this kind of non-compact Lagrangians, like completely supported wrapping is not going to give you somehow transverse intersection point, right? If two Lagrangian are both compact, then what you will see is that you use this completely supported perturbation, you could see a transverse intersection point. But if it's non-compact, you use a completely supported Hamiltonian perturbation. It's not going to perturb it so that it's transverse to itself. If it's not transverse, then there are difficulties in defining the flow cohomology. So that's why for non-compact Lagrangians, what we need is that we need to use non-compactly supported Hamiltonians. And you know, for this Weinstein manifolds, this thing can be regarded as somehow a compact domain union with this somehow half symplectization of its boundary, contact boundary, right? So that's why we have a like R coordinate on the cylindrical end. So natural choice in the non-compact case is that you choose your Hamiltonian to be asymptotic to R squared at infinity. So the effect basically looks like this. So you have like infinite many generators created by this wrapping because your Hamiltonian is non-compactly supported. And all these intersection points are going to give you generators of your Floer cohomology. So this wrapping basically means this. So essentially for like, so this is kind of, the original definition is motivated by the fact that in a cotangent bundle, you have this because in the quaternion bundle, you take the flow cohomology of the zero section, it's supposed to be isomorphic to the ordinary cohomology of the zero section, right? But you want to have something analogous to the somehow chains on the base loop space. When you look at chains on the base loop space, it's going to be like a non-vanishing infinite many degrees and somehow infinite dimensional in certain degrees. That's why you need like infinite many generates. You have a version of Floer theory which is analogous to the chains on the base loop space. So basically wrapped Fukaya category is like this. You have infinitely many intersection points. So this is wrapped. Infinitesimal wrapped is that you do this thing. So this is infinitesimal. So I'd say infinitesimal should. So this is more like
what happens at infinity is you don't have intersection points running away. So there are different ways to do this while getting a consistent pattern. And actually, this like the infinite version. One way of motivating is by mirror symmetry. You know that on the mirror say you have mirrors on the top. Well, there's infinite isomorphism, and you want to reduce on that. So it's not as unnatural as it looks in the first case.
Yeah. Yeah, it's. I think the notion of this partially wrapped and like partial wrapping are all motivated by mirror symmetry. When you have a superpotential, it looks like more natural to have this stop because stop is equivalent to a superpotential basically on the mirror. So you have this two different versions of Fukaya categories. So if you are familiar with sheaves, I should say, you should think of this thing, this infinitesimally wrapped Fukaya category, as consisting of sheaves supported along the skeleton, while this category consisting of objects which are like transverse to the skeleton. So somehow they are kind of, they have dual nature, but they are not always like Koszul dual as the algebras A and B. So let me state the theorem. So we take this endomorphism algebra. We will denote it by B, curly B, of this skeleton L because somehow this category is supported along the skeleton. We are defined to be. So you take all the chambers, all the bounded chambers, and you take the corresponding Lagrangians, and there is this flow cochain complex associated to these Lagrangians. And you take the direct sum of all the flow cochain complex. And of course, you have A infinity structures on this A infinity algebra. So this is a infinity algebra. Not over field, but in this case, over semi-simple ring. So this is basically equivalent to the data of the infinitesimal Fukaya category because I will say later that the infinitesimal Fukaya category is generated by these objects. So the theorem due to.
So in other words, the two kinds of objects, the ones that generate that give you A as the morphism algebra, and those that give you HF, actually live in different categories.
Those give you A and give you HF.
HF, the Koszul dual algebra, they live in different categories?
They live in different categories. One is infinitesimal, one is partially wrapped. A and B, the objects contributing to A and B live in different categories.
So
they're dual.
Not be able to understand eventually Koszul dual algebra is the fact that the set of generators generate in fact the same category because they actually don't live in the same category.
So But I think in this case, it's possible because, I mean, you look at this picture, what we pick for B is are these chambers, right? But what we pick for A are somehow dual to these chambers. For example, this is a cotangent fiber, right? And somehow we need something dual to this one. What is dual to this one is like the sum of these two chambers. And what is dual to this one is this one, right? So it's still possible that they can be related, just for this example. So this is due to myself and Sukjoo Lee and Cheuk Mark. So the A-infinite algebra BL is formal. This formal means that it does not contain higher A-infinity operation. Basically means you have all these A-infinity operations for k larger than or equal to 1, with mu1 being the differential, mu2 being the composition, and mu3 corresponding to somehow Macy product. But formal means that only mu2 is non-zero, but all the other mu k's are 0. Okay. So it's up to quasi-isomorphism. It's such the A-infinity structure is kind of trivial. And there is a quasi-isomorphism. So quasi-isomorphism means you have a map between A-infinity algebras, and it induces an isomorphism on the cohomology. Between this BL, which is built from symplectic geometry, Lagrangian submanifolds inside this hypertoric variety, and the convolution algebra, which you can define using the combinatorial data, or you can define using constructible sheaves. So this is conjectured, I should say this is a conjecture due to Braden-Licata-Phan-Proudfoot and Webster in 2009. Somehow, yes, this is one of their conjectures, I should say. They have conjectures for other hypertoric varieties, which are basically of the same nature. So you have a formality result, which is analogous to this one, and also analogous, I should also mention here, the work by Abouzaid-Smith. Proved, I think in like 2015, the identification between symplectic arc algebra and Kobanov arc algebra. Again, this Kobanov arc algebra is defined combinatorially, and this symplectic algebra is defined in terms of Lagrangian submanifold interior schemes of points over AM mu fibers. And like all the Lagrangians in their definition are like product of spheres. So you have P1 cross P1 cross P1. It basically corresponds to kind of this kind of hyperplane arrangement. So all these are kind of your chambers. They only consider compact chambers. Later it's generalized by Smith and Mark to somehow you can include certain non-compact chambers. But in this picture, we have like chambers. The chambers are possible to be any like a toric final variety. So it's kind of a more complicated version. So it's a interesting question, like because you should have this results of this nature for all the like hypercalar varieties, and you should have like formality results. It's just not clear how to prove like all these kind of results. Maybe there is a way to prove them in general, but I don't know. Currently, it seems to be beyond our technique. So there are other results that I want to state.
All of the Lagrangians you're choosing in your core don't intersect transversely. Is that an issue or not?
They don't intersect transversely, but you know there are like other definitions of Fukaya categories which do not require transversality. For example, all our Lagrangians are cleanly intersecting with each other. In this case, you have a certain combinatorial tool called like Berkeley trees. Basically, Berkeley trees are counting disks connected to each other by like gradient flow lines of some Morse function. So this kind of definition I use, for example, in the working for homological mirror symmetry by Sheridan. And I mean, it's also somehow in FO cubes, they also don't require transversality. So transversality is not that important for the definition. It's just, I mean, you have a convenient way for defining these things. But computationally, I think you almost never compute flow cohomology by using perturbations to make all the Lagrangians transverse. It's better that you use like cleanly intersecting Lagrangians. Another result is the Koszul duality result again. Here I am. So the.
Is this really true? Like if you turn on all the complex parameters you said you turn on?
Right.
Is it not an artifact of your pictures that they thought it was not transverse? I thought you could perturb things, but they actually.
You can always perturb things. That's true. But you need to do simultaneous perturbation so that all the Lagrangians are transverse. It's not about two Lagrangians. You have a collection of Lagrangians. You want to make them simultaneous transverse. That's going to be, you need to be extremely careful when you do this perturbation. Two Lagrangians are always easy. Flow cohomology is always well defined. But when you look at this A infinity algebra, you want to like have a better understanding of this A infinity algebra. I think the best way is not to perturb them so that they're transverse. I don't even know whether it's possible to achieve like simultaneous transverse.
I think people will not have a nicer picture if you were to use different classes of Lagrangians. They're still defined with the same data, but these stable basis guys that are under another class. They're nicer because they all look the same.
Right.
And I think if you use them, then you have a nice small.
Yeah, it's possible. I think.
I mean, unless you particularly care to get Webster's algebra on the node, you'll get something slightly different.
Yes. Yeah. So you may have some problem when trying to match with this convolution algebra defined by those people combinatorially, because if you use a different set of objects and it should correspond to a different algebra, may not be. Yeah. But I think what you said is true. So there is this. So there is also a corresponding Koszul duality result, which is somehow geometric version of the Koszul duality between A and B. So to define this, we need to first specify a kind of a. So we first define this A infinity algebra. So I'll call this partially wrapped.
I suppose it depends what your goal is. Your goal is, of course, to get exactly their algebra on the node. I don't know. But if you just want to get some nice algebra, then I think there should be even yet a different set.
Yes, that's true.
It might be you think like pieces of the, some sub-algebra with the scalar double which are more refined ones.
Yeah, another thing to worry about is I don't know whether like formality still holds, whether it's still formal, because if you change to another basis, because formality is not like preserved if you. Yeah. So this is Yeah, so there is a reason why they conjecture specifically that kind of convolution algebra is related to the Fukaya category, because that should ensure you have formality result. So I will call this partially wrapped Fukaya infinity algebra. So this is defined to be, again, you take the chambers which are bounded in this polarized hyperplane arrangement. But now you look at objects which are dual to this Lagrangian L alpha and L beta associated to the bounded chambers. So by dual, I mean for example, the co-cause of the handles, which you should sort of as like locally, it's like cotangent fibers. Co-cause are dual to cause. And linking disks, you should also sort of as cotangent fiber, now cotangent fiber associated to a non-compact Lagrangian, which is part of the skeleton, are due to stops. Sorry, the Lagrangian is contributing to stops, I should say. So basically, these Lagrangian alpha inside, bounded non-compact chambers. So I should say I denote these compact chambers by K. So if we look at this picture, so this is a compact chamber. But all these chambers are bounded. So these chambers are objects associated to your infinitesimal Fukaya category. But the partially wrapped Fukaya category, you look at dual chambers associated to this picture. For example, this P2 is dual to a cotangent fiber. This Q is some point inside P2. And this thing is a conormal fiber. So this is conormal fiber associated to some P1 inside P2. This thing, because this is a non-compact Lagrangian, it intersects with the boundary. So in the boundary, you have a stop. You could look at the linking disks associated to it. So in the boundary, it's a Legendrian 3 sphere. So it's a linking disk associated to a Legendrian 3 sphere. And here you have a cotangent fiber. If you intersect with the boundary, you will also get a Legendrian 3 sphere. So this is also linking disk associated to this Legendrian 3 sphere. What is interesting is that these two Legendrian 3 spheres, say, so let's say this Legendrian 3 sphere lambda 1. So this is Legendrian 3 sphere lambda 2. So this lambda 1 and lambda 2 actually intersects cleanly along a circle. So this is a singular Legendrian that is in the boundary, and both of them have their linking disks. And what we should look at in this case is this cotangent fiber and these two linking disks associated to lambda 1 and lambda 2. So in this case, we have gathered dual objects correspond to these three chambers, and we use these dual objects to build this partially wrapped Fukaya infinity algebra. So the conclusion of our theorem, so we haven't stated what our theorem is. I mean, you can definitely find these dual objects in the hyperplane arrangement picture. They all correspond to chambers, but some of them correspond to the sum of two chambers. Some of them correspond to not necessarily bounded chambers. theorem. The A infinity algebras A air and B air are Koszul dual. In the sense that if you take the bar construction of this A infinity algebra A air and take its linear dual, what we will recover is this A infinity algebra B air, which we already know to be formal. And you can do the same thing for this A infinity algebra B air. What we will get is this A infinity algebra A air. Or in other words, somehow you have a collection of objects which are built from bounded chambers, and you have a dual collection of objects, and the data of these two collections of objects can recover each other. And because somehow this is, I think this is also noticed in Mina's paper on categorification of knot invariants, there is a result due to Keller, which tells you that if you have two Koszul dual A infinity algebras, A and B, then the causality of B will imply the formality of A. Because in our first theorem, we already identified this B air with this convolution algebra, which we know to be Koszul by the standard result of these people. So we know that this A infinity algebra A, which is built from objects in a different category, partially wrapped Fukaya category, is also formal. So we get a corollary. The A infinity algebra A air is also formal. And we have a quasi-isomorphism. Between this A air, because we already know that this BV is Koszul dual to AV, so this A air, because it's also Koszul dual to AV, so we know that there is an isomorphism between this partially wrapped Fukaya A infinity algebra and this convolution algebra AV that I defined in the beginning of this talk using the combinatorial data of a polarized hyperplane arrangement. So we have these results, and the corollary of our Koszul duality result is the following. So the infinitesimal Fukaya category F associated with this stopped Weinstein manifold is split generated by the collection of Lagrangians associated to this bounded chamber, these bounded chambers. So maybe let me sketch a proof of this split generation result, how it follows from the Koszul duality. So proof. Consider the subcategory. Let's say V, or maybe B, because it's bounded, corresponding to bounded chambers. Inside this infinitesimal Fukaya category. Because we have proved this Koszul duality result of this A infinity algebra B, which is defined in terms of objects in this subcategory, with this A infinity algebra A, we know that there is a derive equivalence, because Koszul duality functor induces derive equivalences, which is the classical result. But in this case, we need to be a little bit careful because this is kind of a new version of Koszul duality, not just a quadratic duality. But still, you have this version of derived equivalence between the derived category of perfect modules over this subcategory B with the derived category of proper modules over this A infinity algebra AL. But we know that by the work of GPS, they prove that this partially wrapped Fukaya infinity algebra is always generated by co-cores and the linking disks. That's why we know this is the same as proper modules over the partially wrapped Fukaya category. On the other hand, we have a natural embedding, because if we look at any object inside this infinitesimally wrapped Fukaya category, you take its morphism with any object in the partially wrapped Fukaya category, it's always going to be finite dimensional because of the nature. Which? Perfect module means triangulated envelope. You have this collection of objects in the Fukaya category, and you want to get a kind of triangulated category. You need to add like twisted complexes, and adding all these things will give you this perfect module. So this is like a smallest triangulated category which contains all the objects inside this Fukaya category.
So there you would pick a set of generators and then say twisted complex will that particular set of generators.
Right. So this is a particular set of generators, and this is all the objects you can build triangulated envelope of this whole category. Yeah. So because every object, if you look at their intersection with objects in the partially wrapped Fukaya category, it's always going to be finite dimensional. That's why this thing embeds in. I think this is also like proved by GPS, but this is not too difficult. So this is GPS 3, I think this is GPS 2. So you know that this thing gets embedded in the partially wrapped Fukaya category. But combining these two equivalence and embeddings, what we get is we get an embedding from the triangulated envelope of this infinitesimally wrapped Fukaya category to the triangulated envelope of this subcategory, which means this subcategory B split generates. Because when you take their triangulated envelope, this subcategory is already contains all the objects in the triangulated envelope of the whole Fukaya category. So this is somehow how Koszul duality could let you to translate the generation result of GPS to a generation result for the infinitesimally wrapped Fukaya category. And in fact, in this case, we also have a Koszul duality for compare Lagrangians. So this is not corollary, but if one considers only compare chambers, so alpha belongs to K inside this hyperplane arrangement, you can build an A infinity algebra. So I'll denote this thing by K. So this is not so related to the skeleton, but so let me say consider this compare Lagrangians.
So just make sure I understand. So in the proof that in the first isomorphism B is proper module on A.
Right. That's by the fact that Koszul duality induces an equivalence, and in this case, you exchanges perfect modules and proper modules. So yeah. because your categories or your A-infinity algebra satisfy certain grading property. For example, in this case, what you need is to know that this A-infinity algebra A is supported in positive degrees. So as long as supported in, non-negative degree, as long as supported in non-positive or non-negative degrees, and it's locally finite, the grading is locally finite, which means you fix a certain degree, it's finite dimensional, then you always have this equivalence. So this is a standard algebraic fact, I think, originally due to Keller or some of his collaborators. So if we consider this only compact Lagrangians, we have an A-infinity algebra. So let's say this is called K of your hypertoric variety M. Then this A-infinity algebra, which defined using only compact chambers. Is Koszul to the fully wrapped Fukaya A-infinity algebra. Which means you take all the co-cos. In this case, you can regard it as all the cotangent fibers associated to the compact toric varieties inside your hypertoric variety. In this CP2 case, you just look at the cotangent fiber. But there are more complicated cases. For example, you look at the arrangement of these 4 hyperplanes, then you have 2 compact chambers, then you need to consider cotangent fibers associated to these 2 compact chambers. So you have another A-infinity algebra, let's say WM. It's built from the dual objects associated to compact chambers. Yes, and you have the Koszul duality between these 2 A-infinity algebras, and basically this tells you that the Fukaya, if you consider Fukaya category of only compact Lagrangians, it's also split generated by those compact chambers. So this is kind of I should say this is a generalization, but both of these. So this generation result is due to like Seidel. In the case when your hypertoric variety is one-dimensional, which means AM mu not 5 because you have long exact sequence. In other cases, I don't think it's no. And this result, this result is in Seidel's book. And this is also due to Seidel using long exact sequence D equals 1. So this is kind of generalization of these facts in higher dimensions. So let me check how much time I have. Half an hour. So I think in the last half an hour, 40 minutes, I'll tell you something about the proof of this Koszul duality, which makes use of some interesting constructions in Legendrian surgery. So the first thing I need to recall is that the partially wrapped Fukaya category in this case is so we care about this case, but this somehow works in very general cases as long as you have a stopped Weinstein manifold. Can be interpreted in terms of Legendrian surgery. What I mean is that consider Weinstein manifold, a Weinstein manifold. You can always write it as a W0 union with some critical handles. So these are Weinstein handles corresponding to critical points of a Morse function of index equal to the complex dimension of your Weinstein manifold. And this W0 is a subcritical Weinstein manifold, which means if you look at somehow the Morse function or the Stein function of this Weinstein manifold does not have any critical point whose index is n. All the critical points have index less than n. So all the symplectic topology or the symplectic invariants are determined by these critical handles because it's subcritical Weinstein manifold. All the invariants vanish. So what you can do is that W is obtained by attaching critical handles along a Legendrian submanifold. Lambda, which lies inside the boundary of this ideal boundary of your subcritical Weinstein manifold. And this partially wrapped Fukaya category. So say in general, you have a stopped Weinstein manifold can be computed in terms of the Chekanov-Eliashberg DGA algebra.
Can you help us non-experts?
Yes, I will. I will recall the definition basically. DGA. So this Legendrian of this Legendrian. Somehow, let me think. So, but still, you have this stop. So this stop somehow, where also you look at its intersection with the ideal boundary of this W0. So you will obtain another Legendrian submanifold. So let's say this is lambda plus, and this guy is lambda minus. So
maybe you can tell us what the surgery means in these examples.
Yes. So the simplest example is you look at you want to construct T star S1, which is a cylinder on annulus if you take away the infinite part. So what you do is that you start with a disk, and you start with a sphere on this disk, which is just given by 2 points, and you attach a handle along this sphere. What you get is exactly T star S1, and you have this core of the handle. So this is the core. So if you have a Lagrangian filling of this Legendrian sphere, which is given by 2 points, but you can have a kind of arc which fills it, which is a Lagrangian filling, and combining with this core, you recover the 0 section. And you also have this co-core associated with this handle, which is this guy. And this is co-core, in this case, is just a cotangent fiber. And you also want to construct a T star S2. What you do is that you need a Legendrian.
Can you help us see how this T star S1?
I mean, this is just this one, right? Equivalent.
Oh,
this,
yes.
This is 0 section. This is cotangent fiber. Yeah. So if you want to get T star S2, what you want to do is that you want to start with a Legendrian inside somehow a 4-dimensional ball. So it's the boundary is like S3, but you can somehow do a little bit perturbation so that this Legendrian lies inside R3, right? It's okay to assume that it's a Legendrian in R3 because it's away from the point at infinity. So in this case, a Legendrian, because it's 1-dimensional in 3-dimensional space, you can do something called front projection. which means you have like R3 with coordinates x, y, z, R3. You project to the x, z coordinates. So in this case, what a Legendrian S1 will look at is something like this. So you have two cusps. And if you want to build T star S3, what you do is that you start a 4-dimensional ball, then you attach a handle along this Legendrian link, attach a 2 handle. Then what you will get is T star S2. And you can consider more complicated cases. For example, A2 Milnor fiber. So A2 Milnor fiber is a plumbing of 2 copies of T star S2. By plumbing, I mean you identify the cotangent bundle, identify what the zero section direction of the one cotangent bundle to the fiber direction of the other. And you identify the zero section of the fiber with the cotangent fiber direction of the first one. So what plumbing would look like is you have 2 Lagrangian spheres intersecting with each other transversely at a single point. Or in terms of Lefschetz fibrations, what you would look at, what you would get is you have this plane C, and then you have 3 critical points associated with this Lefschetz fibration inside this. The map is defined on this A2 Milnor fiber, and you have 3 critical points, and the regular fibers are cylinders, and the singular fibers are union of 2 copies of C. So what you get in this case is that you take 2 singular fibers and you will get a Lagrangian matching sphere. So this is your vanishing cycle, and it vanishes as these 2 singular fibers. So what you can see is that in the base, if you draw these 2 line segments, you will get 2 Lagrangian spheres, V1 and V2, and they intersect transversely at a single point, which is exactly this picture. And if you want to construct this Weinstein manifold, what you need to do is that you need to consider Hopf link inside S3. If you do this front projection picture, it looks like this. So basically what the Legendrian surgery tells you is that all the information in this, I think I haven't talked about the stop, but ignoring the stop, all the information of the replica character of this Weinstein manifold can be recovered from these Legendrians inside not the boundary of your Weinstein manifold, but the boundary of a subcritical Weinstein manifold, which is in our case the ball, the 4-dimensional ball. And the way you recover it is that you look at the Chekanov-Eliashberg DGA associated to this Legendrian link. Additively, the Chekanov-Eliashberg DGA is generated by Reeb chords. So this R is the set of all Reeb chords. So there is a Reeb vector field on the content manifold, and you look at the flow of this Reeb vector field, and the trajectory will end on your Legendrians. So you take all Reeb chords ending on your Legendrians lambda, and you need to take words of Reeb chords, and you allow words of any length. And you can define a differential on this thing by counting holomorphic curves, which looks like this. So these are Reeb chords. So your holomorphic curves need to have one input and all the others are outputs. So if you take, for example, DEA of a Reeb chord, it will give you some words of Reeb chord, B1 to BM, multiplying with each other together. So this defines the differential Chekanov-Eliashberg DGA algebra. And the statement is that if you consider the co-cos Li inside your Weinstein manifold, so these are Lagrangian disks, and you can consider the wrapped Fukaya A-infinity algebra, which is basically taking the direct sum Ij of these co-cos. You get an A-infinity algebra by counting basically holomorphic polygons, right? For example, this thing will contribute to mu4. So the conclusion is that you have a surgery quasi-isomorphism. So this is due to Bourgeois, Ekholm, Eliashberg in the case when there is no stop, and Ekholm-Lekili and Ekholm-Asplund in the case when we include a stop, which is a partially wrapped case. What you get is that you always have a quasi-isomorphism between the Chekanov-Eliashberg DGA associated to your Legendrian, but this Legendrian is like before attaching the handles with this A-infinity algebra. So somehow you can reduce the computation of this A-infinity algebra to the computation of this DGA. And if your dimension is not high, for example, this two-dimensional case, then somehow there is a, in somehow dimension 4, I think so, which means the Weinstein manifold has dimension 4. Somehow there is this resolution construction of Yin, which basically tells you that Yin's resolution will reduce the computation of this Chekanov-Eliashberg DGA to combinatorics. So this basically tells you that, but in higher dimensions there are analogous works, but it's much more complicated. So basically tells you that this wrapped or partially wrapped Fukaya category, it's in some sense computable. It has better properties than the infinitesimal Fukaya category of compact Lagrangians.
So your left-hand side lambda, it only depends on the attaching Legendrian or the boundary of W0.
Right.
And the right-hand side depends on the handles.
So the co-cos of the handles. Right.
And you specify with lambda plus, lambda minus, which one you choose to get off.
So I'll take this hop link example as an example. So for example, we specify this this thing as a plus, this thing as a minus. So if we specify it like this, then lambda plus will basically will serve as the stop. And lambda minus is where we attach the handles. So if we as we have seen, if we regard both of these as lambda minus, then we attach handles with A2 mu naught fiber. But in this case, if one Legendrian or not is labeled as plus and one is minus, then what we will get is S2 stopped at lambda minus. Sorry, stopped at lambda plus.
So you
Right, everything is lambda minus in that case. And if lambda plus is non-empty, then this Chekanov-Eliashberg DGA needs to, I mean, you need to consider this Chekanov-Eliashberg DGA over loop space coefficients. Sorry. So coefficients lies in chains on the base loop space of your lambda plus. So
sorry, dimension 4 is dimension real dimension?
Real dimension. Yeah, so everything reduces to, I mean, you can project it to R2. So you have 3-dimensional content manifold.
Yeah, so in that dimension, yes, it's clear that everything is trivial, but how do you go to higher dimension?
You go to high.
I see in a hypertoric case, probably somehow still.
Yeah, so the reason is that we don't need to compute the Chekanov-Eliashberg. In higher dimension, you have other works like there is this Rutherford-Sullivan.
But somehow, for your purposes, knowing basically the trivial case is enough. Exploiting my topic, right?
So for my purpose, you need to deal with higher dimensions, but you don't need to compute the DGA. I mean, you only need to like conceptually argue that there is Koszul duality. You need to what you need is that you need some information about gradings, but you don't need to compute the whole DGA.
But how do you get any information on grading? I mean, but in particular, Koszul grading, you don't know, right?
Koszul grading you don't know, but in this case, it's kind of easy.
I think from physics, it is completely, there's a simple way of understanding Koszul grading. I think from what Sandra Tang and Ishon know, you can simply determine all the grades.
Yes. Somehow, I mean, you can also like argue combinatorially using the properties of a hyperplane arrangement. I mean, so you don't even need to know the grading of every generator. You only need to know some like locally finiteness of the cohomology of the Fukaya.
Because there's no grading in
the thing is that in this case, the original naturally defined geometric grading on the Fukaya infinite algebra is enough for the Koszul duality. You don't need an additional grading.
Sorry, the naturally defined grading is enough for grading?
Yes. So this grading, if you take its Koszul dual, you already recover the other Fukaya infinite algebra. You don't. Some cases you need an additional grading, but in this case you don't. Yeah. So. So I'll explain, because I have said before that in our case you need to deal with this singular Legendrian. For example, in our case, lambda plus is non-empty, and what I should say is that it's singular. So as I have said, in the case of cotangent bundle of P2, it's a union of two S3s along a circle. So this is a singular Legendrian. Which means the original setup of Ekholm-Lekili is too restrictive, because they require this lambda plus to be smooth, and which correspond to the fact that the Lagrangian skeleton, the components of the Lagrangian skeleton should intersect transversely. In our case, it's not transverse. For example, the singularity comes from the fact that if you look at these two chambers, they intersect cleanly, and this clean intersection, they somehow intersect with the ideal boundary. That's why in the boundary you still get a clean intersection, which is an S1, but here you get a clean intersection, which is a copy of C of the complex plane. Okay. So that's why we need some construction which replaces this singular Legendrian with a smooth one. So basically, this construction is due to Asplund-Ekholm. Somehow we combine this construction of Asplund-Ekholm in the work of Legendrian surgery with the setup of Ekholm-Lekili when dealing with like duality between Lagrangian and Legendrian invariants. This enables us to generalize the setup of Ekholm-Lekili to the case of singular Legendrians. Okay, so what we do is that we have this, in general, we have this Weinstein domain M bar. Weinstein domain means we remove the cylindrical end. And we have a singular Legendrian. So let's say the components of this singular Legendrian, let's say it's a little bit hard to draw. So this is your Legendrian, lambda v. So what we do is that because all the intersections, I mean this singular Legendrian lambda plus is going to be a kind of a union of a set of Legendrians lambda alpha, and this set of Legendrians lambda alpha, they have like singular intersections. So all these intersections happens inside a subcritical Weinstein domain inside the boundary. I should say subcritical Weinstein hypersurface inside the boundary of your manifold. The reason is that if you look at this singular Legendrian, lambda plus is the skeleton of a Weinstein hypersurface. W inside the boundary of your original Weinstein manifold M. So originally this is a Legendrian, but somehow we lower the dimension by 1, it's going to be a Lagrangian, and it's going to be a Lagrangian skeleton of a Weinstein hypersurface, which is 1-dimensional lower in this contact manifold, which is the ideal boundary of M. So what we know is that because it's a skeleton of a Weinstein hypersurface, we know that all the singular intersections happens inside this W0, which is the subcritical part of your Weinstein hypersurface. So what we do is that we have this Legendrian, which you should think of it as like this lambda v shifted up a little bit to this boundary of your Weinstein domain M. So what we do is that we consider only the part, the Lagrangian core disk, which is outside of the subcritical Weinstein domain, and we denote this thing by dv. So this is a disk, and we have removed all the intersections which happen inside this WZ. Lambda v is one of the components inside this lambda plus, which is a singular Legendrian which serves as a stop. To give you a more clear picture, so this is, for example, this is a subcritical part, and you have some intersection of the Legendrians, right? But what we do is that we do not look at these intersections. We only look at these disks, dv, right? This is also a dv, and it looks like these dv intersect, but in higher dimensions they don't intersect. So what you can achieve is that only look at the cores of the Lagrangian core disks of your handles. Because there is one additional dimension, so that you can achieve that these things don't intersect. Then there is another space, which is basically the simplexization of W. So this is just a minus infinity, which is half line times R times W. And in this picture, you also have this Weinstein hypersurface because it's constructed from this Weinstein hypersurface, and still we have this W0. So this is W0. And again, we have a copy of this Legendrian lambda V. And what we do is that we remove what happens inside this subcritical part W0. And what we keep is that this Lagrangian disk TV, Lagrangian with respect to this W. So what we do is that we attach a handle, we attach a W0 handle. So this is W0 times a very small disk cotangent bundle over -1, 1. So once we attach this handle, we get in some sense a Weinstein cobordism with positive boundary somehow constructed from this ideal boundary of this M, and this boundary, which is 0 times R times W, and connected by a Weinstein handle. But there are also a negative boundary, which correspond to this N. So in this sense, this Legendrian, this Lagrangian disk, we can see that it goes through this handle. So we can basically, we take 2 copies of this dV, and what we get is that we can connect them together. I hope this picture is okay. When we connect them, these 2 copies of dV together, you get a copy of the Legendrian sphere. So what we do is that we have a Legendrian sphere. Which replaces the original lambda V. And this Legendrian sphere, which we denote by sigma V, is given by this dV union the boundary of partial dV times -1 to 1. So it goes through the handle and takes the union of dV again. So this is going to give you a Legendrian sphere. And the good thing is that this collection of Legendrian spheres, they don't intersect with each other. Link, so it's a link of Legendrian spheres. So the original intersections, which is inside this W0, because we have removed this W0 and replaced it with somehow a handle. That's why the original intersections inside this subcritical part no longer appear, but instead we get a collection of Legendrian spheres which are disjoint with each other, but inside the new contact manifold. And inside this new contact manifold, all the information that contained in this singular intersection are replaced by some Reeb chords, which happens inside this new boundary. So we can replace lambda plus with this new collection of Legendrian spheres, and we define the Chekanov-Eliashberg DGA to be the Chekanov-Eliashberg DGA. So we keep lambda minus part invariant because singular intersections do not appear in this part. And you take the disjoint union with the sigma, where sigma is the disjoint union of this Legendrian spheres, sigma phi. So this will give you a well-defined Chekanov-Eliashberg DGA in the usual sense. And the good thing is that there is a quasi-isomorphism between the partially wrapped I say partially wrapped Fukaya infinity algebra. Of the stopped Weinstein manifold. In our case, it's M. So the stopped Weinstein manifold is you need to attach handles along lambda minus and keep lambda plus as a stop. Using this. So it's just you have a quasi-isomorphism. Yes, it's a generalization of Legendrian surgery for singular Legendrians. So you still have this quasi-isomorphism between this, right? Because the singular Legendrian does not affect the definition of partial.
What's the category? My question is.
So the space is M minus lambda minus is M. Attach handles along lambda minus.
So that's the best before.
Right, but there is this additional lambda plus which serves as a stop. But we assume that this lambda plus and lambda minus are disjoint. That's why this lambda plus after attaching handle is still defines the Legendrian inside this new boundary, which is the boundary of M with handles attached along lambda minus.
So sigma is leaving the original boundary or
sigma is not living in the original boundary or new boundary. Sigma is living in the boundary of this, living in the positive boundary of this Weinstein cobordism, and there is a negative boundary. But you can do a little bit analysis which shows that the holomorphic curves, they don't go to this end. It's always this half. So it does not affect the definition of Chekanov-Eliashberg DGA. So this is how you can deal with singular Legendrians, as in the Hypertoric case.
Okay, do you want to summarize for us? I'm getting a little bit high. If there's any important points, just to make sure that I don't miss something.
Okay, so important points. So maybe I'll summarize because I've told you how this construction of the you replacing singular Legendrians with non-singular ones work. So I'll give you a table which basically relates what happened in this general setup where singular Legendrians appear and what we have in the Hypertoric case. So this is general, and this is Hypertoric. So we have this, in general, we have a subcritical Weinstein manifold. So in our case, we denote it by, say, M. And in the Hypertoric case, we have some subcritical part, I'll denote by N inside this M. So there is a collection of Lagrangian so there is a collection of index set, right? There is a lambda equals lambda minus disjoint union with lambda plus. And here we have somehow, the Legendrian comes from the intersection between the Lagrangian skeleton and the ideal boundary. So basically this Legendrian, so I will first write this. So this lambda b means you somehow the Legendrian associate all the bounded chambers which plays the role of this Legendrian. This lambda k correspond to this lambda minus because all the cocors correspond to like compact chambers. And this bounded but non-compact chambers, they correspond to stops. So this part is singular and this part is singular. And we have this stopped Weinstein manifold, m lambda minus lambda plus. Here we have this our familiar stopped Weinstein manifold. This is the correspondence between the general case and the hypertoric case. So in this way, we can use the general setup of Ekholm-Lekili, and we do some kind of grading computations, and we have the Koszul duality. Okay, so I think I should stop here.
Thanks again for the wonderful talk. Questions? Okay. Yeah.
So on one side of your story, you should have just all the master gradings are trivial if you get associative algebra, right? From what you had written.
Just associative algebra is also Z-graded. It has non-trivial gradings.
But that grading you say you can somehow get from geometry?
Right. You can get it's exactly from geometry.
But that's not a muscle grading. Because the muscle gradings are trivial.
No, the Maslov, what I understand is you have Maslov grading of this Legendrian, but the Maslov grading of this Legendrian is non-trivial. It's somehow negatively supported in non-positive degrees, but there are non-trivial grading, infinite many non-trivial gradings for this Chekanov-Eliashberg DGA. It's just for every fixed grading, it's just only finitely many generators.
Okay, so somehow there is some other grading that's somehow obvious from this Eliashberg story.
Right.
And you say positivity of these gradings is obvious in the setting, or?
So positivity of gradings, I think there are various ways to see this. You can use Legendrian surgery, or you can say that because we already know this Koszul duality, right? You partially wrap this Koszul dual to the infinitesimally wrapped, and we have identified this infinitesimally wrapped with the convolution algebra, which is non-negatively graded. That's why its Koszul dual is non-positively graded. So their gradings are related.
So when you say the grading of this, say the A algebra, the grading is the cohomological grading or some other grading?
Cohomological grading.
And another question, like here, so why is it's very nice and beautiful that you can relate to that category with this Chekanov-Eliashberg DGA. What does it? How do you use that relation here?
So the reason you need to use this relation is that the part that we need to use Ekholm-Lekili is that they can write this Chekanov-Eliashberg DGA as the cobar construction of something called the Legendrian co-algebra. Legendrian co-algebra of some of your Legendrians. So this Legendrian co-algebra is actually the linear dual of something called a Legendrian A infinity algebra. But this Legendrian A infinity algebra is by definition the endomorphism of your infinitesimal Fukaya category. So by using Ekholm-Lekili, what we can get, so remember that Koszul duality requires like the Koszul dual of A is equal to B, and the Koszul dual of B is equal to A. So by generalizing this setup of Ekholm-Lekili, we already have this equivalence, but we only need to prove the other equivalence. But there is some theorem saying that once you have this equivalence and certain grading conditions are satisfied for this A and B, then you will automatically get from this equivalence this one. So what we need to do is just to ensure that the grading restrictions are satisfied.
So in short, Koszul duality follows from the generalization of the Lekili and Ekholm.
Generalization of the setup and some other arguments.
But it doesn't seem like you understand the grading fully. You rely on Koszul duality to say you know the gradings, but you need to know the gradings to know Koszul duality. So
We don't understand the grading is 40. We only know it's locally finite. Fixed degree, it's finite dimensional. That's enough.
Would it be helpful to have some like direct understanding of the grading?
Direct understanding of the grading, yes. I think if you start with the Chekanov-Eliashberg DGA, you can prove that it's kind of, I mean, in many cases you can prove it's non-positively graded. So it's geometric that your Maslov grading is always, I mean, so there could be some generators which have like positive Maslov grading, but you can always cancel these generators.
And yeah, and your equivalence, you say that quasi-isomorphism, so it's not unknown that you compute them in the same. You say, well,
it's not, you said that you computed it's the same, right? So, I mean, if you have this equivalence and you want to deduce this one, in general, what you get is that you will get a completion here. I mean, you need to take the completion because you know in the Chekanov-Eliashberg DGA you have words, so you can complete with respect to the length of the words. So in general, you only get these two equivalents. So this one, which follows from generalizing setup of Ekholm-Lekili, and this one, which requires you to have a completion of this DGA algebra. But the question is how to remove this completion. But you want to remove this completion, it's enough that it's locally finite. The grading is locally finite. So the completion is isomorphic to itself. So this is a complete DGA algebra. So you know there is Koszul duality. In general, we always have these two, which is basically follows from generalizing the setup of Ekholm-Lekili.
We should leave more questions after this. Okay, thank you again.